Hey guys, Mr. L coming back at you with another video. And in this video, we're going to talk about chemical equations as well as different types of reactions. So we're going to talk about mass relationships, the basis of stoichiometry, how to balance a chemical equation and the structure of a chemical equation, as well as the different kinds of reactions that exist, or the main major categories. So let's get into this video. So the first thing we're going to talk about is the basis of stoichiometry. So stoichiometry comes from Greek, which means to measure amounts. And when we're talking about chemical equations, particularly stoichiometry, we're interested in the mass relationships or molar relationships between different reactants and products, or different product formation. So we're going to have to study how much stuff we have at the beginning of a reaction and how much stuff we have at the end of a reaction. And we should have the same masses from beginning to end. We can't create or destroy matter. And that's based off of the law of conservation of mass. And again, Einstein showed that we can relate mass to energy. So we also have the law of conservation of energy. So we can't create or destroy matter, basically, is the point of this. So the first guy that really started to study this was a French chemist named Antoine Lavoisier. And he would go in the lab and he would study the mass relationships between different reactions, mostly in the gas phase. So let's start to discuss what a chemical equation is. A chemical equation is a concise representation of both particles and molar values. So we have this equation that tells us the stuff we're going to need in order to react to produce some other stuff. So the stuff that we're going to need, or the precursor, are called our reactants. So on the left side of the yield, which is the arrow or the chemistry equal sign, on the left side of that we have reactants. And in this example, we're going to combust some hydrogen gas and oxygen gas to form some water particles. So our hydrogen gas, our two particles of hydrogen, are going to react with one particle of diatomic oxygen, and these are going to be our reactants. Then we're going to have this arrow in the middle, which is called the yield symbol. And then following that, we're going to have our products, or whatever we're going to produce. In this case, it's water. So we could see that we're going to need two hydrogen particles for every one oxygen particle, and we're going to be able to produce two water particles. And the reason why we're putting these numbers in the front is so that our masses of all the elements combined are going to be equivalent. If we were to add up the total mass of hydrogen, we have two H2 particles for a total of 4 grams per mole, or 4 AMU. We're going to have one diatomic oxygen particle at 32 grams per mole, or 32 AMU. So we got 32 plus another 4 is 36. If we look at our water particle, water's got one oxygen worth 16 and two hydrogens worth another 2, so that's 18. And if we multiply that by the 2 that we produce, we have the same exact value as the amount of our reactants. So we're balancing our mass by using these different chemical equations. So when we're talking about chemical equations, such as the one that we have here, where we've got methane gas reacting with diatomic oxygen gas to release carbon dioxide and water, you've got many pieces on here that need to be there to have a proper chemical equation. The first one that you're going to have are chemical formulas. So you're going to know the proper formula based on your naming rules. And if you haven't memorized your naming rules, you can go back to a previous video and see how to properly name compounds. So that we know the name, we can come up with the chemical formula, and we can start using numbers or mass values. So we got some chemical formulas. We have CH4 for methane, we have O2 for oxygen, CO2 for carbon dioxide, and H2O for water. The next thing we're going to have is our reactants on the left and our products on the right. On each of these formulas for our products and reactants, we're going to have to put phases on there. And there are 4 primary phases that we're going to use in this class. We've got solid, symbolized by little s in parentheses after the formula as a subscript. We have L for liquid, G for gas, and AQ for aqueous, which means that substance has been dissolved in water, so water is implied there. The next thing we're going to have are coefficients. And it's very important that when we go to balance chemical equations, that you put the coefficient in front of the molecular chemical formula. So what the coefficient is telling you is how many of those overall particles that you have. So in this equation, we've got a 2 in front of O2 particles. So that means we have 2 O2 particles. You can't ram the 2 in the middle or at the end because it's going to change the meaning of this. If we were to drop the 2 behind O2, then it would seem like we have 22 oxygens within one particle, and that is not the case. So we put our coefficients in front of the chemical formulas. We also have a 2 on water, so we have 2 water particles. If there isn't a number in the front, then it's implied that we have a 1. So like methane and carbon dioxide are implied that we have 1 of each in terms of this reaction. The coefficients can represent 2 different things. It can represent a single particle example, so we'd have 1 particle of methane reacting with 2 particles of oxygen, or we can relate them to molar values. And a mole is Avogadro's number of particles, which is 6.02 times 10 to the 23rd. So if we had 1 mole of methane, we'd have an Avogadro's number of particles. And if we had 2 moles of oxygen gas, we'd have 2 of those. So we'd multiply Avogadro's number by 2. So those coefficients represent 2 different values, but we can simplistically just write this as a chemical equation. So when we go to do this, when we go to write chemical symbols and coefficients in the front, the whole point of this is so that we can balance our mass so that we don't create or destroy matter. As well as we can count the number of atoms. So when you go to do this, the best way to see if it's properly balanced is if you just take an accounting of how many atoms you have in the product side, how many atoms of that same element you have in the reactant side, and they should be equivalent. So we can just apply these to either single values or molar values. The last thing we're going to talk about in this video are the different kinds of reactions or major categories of reactions that we have in chemistry class. So a lot of times these different categories are spread throughout the textbook, and I'm just going to compile them all into one little video here to give you 6 major types of reactions that we come across in chemistry class. The first one we've already seen an example of, and that's combustion. So combustion is where we take something and react it with oxygen to release carbon dioxide and water, typically. So if you see something plus oxygen gives carbon dioxide and water, that's an indicator that you're burning that substance or combusting it. Humans and other organisms that use the glycolytic cycle and the Krebs cycle, we also are essentially combustion engines. We take in carbohydrates and fats, and we breathe out carbon dioxide and water vapor. Especially on cold days, you can see that water vapor condensing in front of your face. So this is a type of combustion reaction. A big indicator that you have a combustion reaction is if you release a lot of heat and light in the form of fire or some other light source. The second type of reaction we have here is a combination reaction, or some other textbooks call this a synthesis reaction. So if you take 2 substances and you form something new, then this is a synthetic reaction. So in this example we have here, magnesium ribbon or magnesium solid is going to react with oxygen gas to form magnesium oxide. So we're synthesizing or combining 2 to make this new 1 particle. So typically if you have a reduction of particles or you're combining things, this is a combination reaction. The third type of reaction we're going to talk about is almost the opposite of combination, and that's called the decomposition reaction. So if we were to have a compound such as calcium carbonate and we were to heat this, we're going to be left with calcium oxide and carbon dioxide. So we're going from 1 crystalline reactant, heating it, and we're getting 2 products. So we're breaking this thing apart. We're decomposing this. Another example of this is sodium azide, which is located as crystal structures in the center of your steering column. When you get in a wreck, that sodium azide quickly decomposes to release nitrogen gas, thus inflating your airbag. So this is an example of decomposition in the real world. The fourth category, we're going to spend a whole video series on this, are going to be acid-base reactions. And the general formula for this is if you've got acid plus a base reacting, you're going to form a salt and water. And this is a special kind of double displacement, which is another category we're going to talk about in a second here. But it's a very specialized double displacement reaction that's unique, and usually it gets its own chapter in textbooks, or maybe even a chapter and a half. So acid-base reactions are going to have hydroxides or protons, and those are going to react to form water. And usually your net reaction is going to be the formation of water for an acid-base reaction. So that leads us to our fifth type of reaction, and that's going to be single and double displacement. And the way I like to think about this is you have dancing partners, especially for double displacement. So you're dancing with a partner and somebody next to you is dancing with a partner, and then you're going to swap partners and dance with the new partner. So in the case of our acid-base reaction, we have sodium hydroxide and hydrochloric acid. We're going to switch out the positive ions with each other. So sodium is going to pair up with chlorine or chloride ion, and hydrogen is going to pair up with hydroxide, forming water. So we're just going to swap the fronts out or the backs out. Typically, you're going to change phase. So you're going to see phase change between different things, and that's going to indicate you have a reaction. And the common products of a single or double displacement are going to be precipitates, which are solids crashing out of solution of two aqueous solutions, or you're going to form gases, so you're going to see bubbles occurring, or in the case of acid-base, you're going to form liquid water from aqueous substances, so that's technically a phase change. So the last type of reaction we have is called a redox reaction, and that's short for reduction-oxidation reaction. Reduction is gain of electrons. So if you have some element within a reactant and at the end its oxidation value has gained electrons, that's going to be reduction. Oxidation is loss of electrons. So if something went from oxidation value of 0, like pure sodium, and then in a compound it's got a +1 charge, so it's gone from 0 to +1, it's lost 1 electrons, then it's been oxidized. So when you have a redox reaction, you have to have both occurring at the same time. Something's got to be losing electrons in order for something else to be gaining them. So we call these redox reactions. And we talked about the formation of magnesium oxide when we were talking about combination reactions. This is also a form of a redox reaction. Magnesium has an oxidation value of 0 as pure magnesium. Pure oxygen also has an oxidation value of 0. When we go to react these together, we form magnesium oxide, which is an ionic compound. And we know that magnesium ion has a +2 charge, so it's lost 2 electrons. Magnesium has been oxidized in this process. Each oxygen has gained 2 electrons to form oxide ion. So oxide ion has gained 2 electrons. It has then been reduced. So the best mnemonic to remember this is oil rig. Oil, oxidation is loss, rig, reduction is gain. And remember, they have to go hand in hand. So there it is, you guys. There's a video on mass relationships, how to come up with a chemical equation and balance them, and the different symbols we have, as well as the major kinds of reactions that we have. So if you enjoyed this video, smash the like button, send it to your favorite fungi, send it to your favorite bacterial colony, and we'll see you in the next video.